All right, so in this tutorial we're going to introduce the concept of angular kinematics, which is related to linear kinematics, same type of equations, just slightly different measurements that we make when we're talking about rotation as opposed to moving forward. All right, so the three measurements we want to introduce are angular displacement, angular velocity, and angular acceleration. Like I said, the equations we develop are exactly analogous to the linear parts, and then there's an important bridge between them to allow us to go back and forth between, let's say, linear velocity and angular velocity. There's a lot of little detail in this. Nothing's really new, but jot down ideas or notes or questions you have to bring into class, because we're not going to spend time reviewing tomorrow. We're going to pick up right where we left off with the expectation that if you have any questions, you'll ask them and we can move forward. Okay, so let's take an idea of a wheel. Let's say this circle right here represents a wheel that goes round and round and round. As it goes round and round and round, and it goes forward and forward and forward, we can talk about how fast it's moving forward, velocity-wise. We can talk about the displacement forward, etc. But another thing we can look at is the angular displacement. In other words, how many degrees or radians it has moved every time it makes a revolution or a partial revolution or some combination thereof. So we're going to introduce the concept of angular acceleration angular displacement. It is not the same as just an angle between two lines. It's basically, if you read the definition, how far an object is rotated from a given position. So if this wheel makes one revolution, it will go a distance forward equal to its circumference, but it will go around 360 degrees. If it makes another revolution, then the total angular displacement will be 720, and so on and so forth. Okay? So we often measure angular displacement, not so much in degrees, but in radians. We should be familiar with that from math. So we call them rads. And the definition of angular displacement, theta, is how far you travel. That's your arc length divided by the radius of the circle. Okay? So I'll leave that to you to review from math why that would be. That's something you should learn in very basic trigonometry. Other units you should be familiar with, because we don't always express them in radians, are degrees, as I mentioned earlier, or revolutions. Okay? They're all related, but they say something slightly different. And a key, very important set of conversion factors, something you should be already familiar with, but let me remind you here, is that one revolution is 360 degrees, which corresponds to 2 pi radians. Okay? Half a revolution, 180 degrees, or pi radians. So a simple little example to take advantage of that. Let's say we have a bike of a certain diameter. It rotates through 28.3 radians. And I want to know how many revolutions that is. This is theta, so we got to recognize what our variables are. This is diameter, so I'm going to write in r as 0.34, because normally we want radius and not diameter. And then we're looking for revolutions. So we can't necessarily use our theta equals s over r right away, because that doesn't have revolutions in it. But we do have a conversion factor between radians and revolutions, so that's how we start off. So I'm going to say 28.3 radians, rads, and then my conversion factor right here is that one revolution corresponds to 2 pi radians. Okay, and I'm lining up my units so that the radians cancel out. And if I take 28.3 divided by 2 pi, we don't want to leave our answer as in pi units. Okay, work that out, and you get 4.5 revolutions. Okay, so it doesn't matter what the radius of the bike is in this case. 28.3 radians is always 4.5. Now if we ask how far has it traveled, that's s in the equation above. That does depend on the radius. The bigger the tire for a certain number of revolutions is going to go a lot further. So we would say that theta is s over r, so s is equal to theta r. Okay, plug in the numbers. I'll let you do that. And if you do things correctly, we should get 9.6 meters forward. All right, so that's a decent amount for 4.5 revolutions. Next, when something is rotating, it has a certain speed associated with it. There's a linear forward speed based on distance and time, and then there's a corresponding angular velocity, which is given the symbol omega, a W with a little squiggle in it, that looks at the rate at which it rotates as a whole. Okay, so if we look at this again, the angle is here right now. After some time, it's going to increase, 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 And so it's going to increase with time, and if the object is moving at a constant velocity, then the angle should increase linearly with time. So without going through the whole graphing of theta versus t, or excuse me, angular displacement versus t, and the slope would be the angular speed, we can define it as the theta over r. And units are generally radians per second. It could be revolutions per second. It could also be degrees per second, but the standard is radians per second. Now, before we do simple examples of this, we want to establish a very important relationship between angular velocity, omega, and tangential velocity, v, what we normally call linear velocity. So in this diagram right here, we can say when it goes from this point to this point, it's moved through some angle theta and has an angular velocity. It also has a tangential velocity at the same time. Okay, so it's a fairly simple derivation. If we define, again, omega as theta over r, and theta we saw from above is s over r, then omega is going to be s over r divided by, sorry, this should be time, divided by time. Okay, if I simplify that, that's distance divided by time times r. I'll leave it to you to work on that simplification. And distance divided by time is nothing more than velocity. So we can say that omega is equal to, I'm sorry, I've got the r's in the wrong place. Oops, silly me. So this would be v, or s over t divided by r. So omega is v over r, or tangential velocity is omega r. And that's a relationship we're going to come to again and again and again. Okay, so let's do a simple little example here. We have a marble rolling forward with a velocity v and an angular velocity omega. Okay, it has a radius of 1.3 centimeters, and it takes 0.67 seconds to make one revolution. What is the angular speed in radians per second? Okay, notice we're given one revolution, so we got to convert that to radians first. So that's pretty simple. One revolution is 2 pi radians. And you might ask, well, how am I supposed to know to do that first? Well, if we're looking for angular velocity in radians per second, then that's our conversion factor. All right, from here it's pretty straightforward. Okay, I would say that omega equals theta. Theta in here is 2 pi radians divided by the time. The time is 0.67 seconds. So if you do 2 pi divided by 0.67, you get 9.4 radians per second. And then we can ask, how fast is it moving forward? Okay, that's velocity. That's just distance divided by time. Now, we're given a radius, so we could figure out the distance it travels based on one revolution. We could do pi r. But the more straightforward way, based on our answer here, is we could just say v equals omega r, because we just found omega. So that'd be 9.4 radians per second, multiplied by 1.3 centimeters. And so radians are really dimensionless, so it ends up with centimeters per second. So 9.4 times 1.3 is 12.2 centimeters per second. Okay? So like degrees, radians is dimensionless, so it doesn't have to show up again. And a common way of expressing angular speed, okay, and we saw it here, is to relate it to frequency of rotation. Okay, so we're going to put a little bit more twist on that, and frequency is given a symbol lowercase f. So for example, and it's measured in revolutions per second. All right, so in the previous problem, our angular speed was radians per second. That's the standard, but sometimes this makes more sense to relate things in revolutions per second. And again, if we have one revolution is 2 pi radians, then it would follow that omega, okay, which is, again, let me go back over here. Omega is theta over t, okay? And one revolution corresponds to 2 pi over t, okay? So that's one way we can do it. So theta, or omega, would be 2 pi all over the time, and that's also equivalent to 2 pi f. So I guess that's something we haven't established yet, and I take it for granted. So an important thing to realize is frequency is equal to 1 over period, the reciprocals of one another. Okay? So we'll play more on with that later. Now, I'm going to show you this demonstration tomorrow, but let's say we take a fan and I figure out, and I'll show you how we can figure out with the strobe light, that it is going around and around and around, and its revolution and its frequency we determine by strobe light is 62.5 revolutions per second. Okay, I want to know what the angular speed in radians are. Now I could do a bunch of conversions, but if I use this equation, it's nice. I can say simply that omega is 2 pi times the frequency. Okay, 2 pi times 62.5 revolutions per second gives us 393 radians per second. I suggest that you do this the long way, converting 62 revolutions per second to radians and then doing what I just did there to convince yourself that this turns out the same way. The 2 pi f is a shortcut way of doing it. And then we can ask, how fast is any point on the outer edge of the blade moving if r is roughly 50 centimeters? Okay, now I'm not exactly sure what the radius of the fan blade is, but we can look at that more tomorrow. Again, v is omega r. So 393 times 50 centimeters gives us that it's moving about, that's pretty staggering, 196 meters per, centimeters per second. Okay, so it's moving almost 2 meters per second around and around. That's it for angular velocity.